let's get started. We're going to be a really cozy group today. Maybe some of you want to move down. Do you want to move down? Take 2 minutes. Thank you. So no updates yet on the midterm. Grading is underway. You should have that to you before too long. Congratulations on surviving, though I hear it wasn't too difficult, so that's good news. Topic for today, we're moving on to transport and TCP. In particular, we're going to focus on two questions. What does the transport layer do? And then specifically the design of TCP. And as you'll see, once we get into TCP, we start getting pretty specific and in the details. So I'm going to try and drag out the kind of more general discussion for a while before we get into the specifics of TCP. So with that, the transport layer. We've talked about the transport layer already. We've put up this figure where we said, the transport layer implemented at the end host, usually in the operating system, between the network layer and the application layer. We're going to dig into that a little bit in a little more detail. What this looks like, also, we've covered this, but just to recap, is that at the transport layer, you can have multiple transport layer protocols. So TCP, UDP, SCTP, but there is a longer list than this. So unlike IP. And you can simultaneously, at your end host, you can have multiple flows or applications talking to the network or to the internet, going through different ones of these transport level protocols. They all go through the IP layer, but above that at the layer 4, you can have multiple flows going through any one protocol implementation, so like TCP, but you can also have different applications talking to different transport layer protocols. Okay. So simultaneously in your end host, as shown here, you can have different applications talking to different transport layer protocols, multiple applications using the same TCP implementation, and so on. We've said this as well in the past, but I want to reiterate that the role of the transport layer is to bridge the gap between the abstractions that the application level wants, or people who write application level code, the abstraction they want to work with, versus what the abstractions that the network can support. And again, we've said this in the past, we build our transport layer into the operating system because it kind of acts as a common service for all applications. If we didn't have the transport layer or something like TCP, every application would have to deal with all the idiosyncrasies of what we get from the internet or the network layer. Okay, so let's dig into that a little bit more. What exactly does this mean? So if you look at your application layer, your application code, right, what goes into that application layer? You have all of your application logic, of course, your ML computation, your key value stores, whatever it is you're doing at the application layer. But from a communication standpoint, you do also have these application layer protocols, but they're designed and defined to service the needs of that particular application. Okay? So if you look at some of the examples of application layer protocols, and there are many of them, we're going to study HTTP, but there are many application layer protocols. Look, even just looking at the name, you see something like file transfer protocol. It's a protocol defined for file transfer. Or the network time protocol. It's an application layer protocol that's designed and defined for time synchronization. Right? So they're pretty specific. They're designed for a particular application-specific need. At the network layer, however, we had a very minimal abstraction, best effort delivery of a packet, an IP packet. So everything you need to bridge between this kind of application-specific communication protocol and what the network gives you goes into the transport layer. And as you'll see, there's a little bit of a shift in attitude as well. So when we were designing IP, we were going for this very minimal, very clean interface. We don't want to put anything that's not needed into the network. When we start to design things like TCP, there's a little bit more of, would it be useful to applications? And if it's useful, it's plausible to implement it at the transport layer. Okay, so with that, what does the transport layer address? We've actually covered all the pieces that are needed in various discussions. I'm going to just want to pull it in one particular place. Anyone remembers some of the things we said the transport layer has to do? Yep. Reliability. Others? I think I have 5. Okay, the first one was Demultiplexing. We always have this as we go up the stack, right? Which application, when you receive some data from the other endpoint, you have to know which application does this data go to. So that's the demultiplexing rule. We actually touched on this with the idea of ports in lecture number 3. Reliability, that was our last lecture, and we'll revisit some of it again. Translating from packets to application level abstractions, right? We said applications don't want to think in terms of packets and IP headers and all of that. So we're going to think of what abstractions an application layer wants to think about, and then translating between packets and that is going to be the job of the transport layer. Anything else you remember? There were 2 that came up very briefly when we talked about reliability. When we talked about sizing windows. Everyone's in midterm lab. Okay, so we said that we want to pick the amount of data that the sender should send should be picked with paying attention to 2 considerations. One is you don't want to overload the receiver. We're going to cover this in today's lecture. It's something we call flow control. And the last one was we said we don't want to overload the network. That's a topic that we call congestion control. We're going to have multiple lectures on that. Okay, so let's first talk about how we do these issues in general, and then we'll get to how TCP specifically implements them. Any questions before I go forward? Okay. So first, the question of demultiplexing. If you remember from, and again, what is the problem here? The problem is I've received traffic coming in from the network. It's been passed from your network interface card up into your operating system. It's gone through the IP layer. At the IP layer, we looked at a protocol field and said, this is TCP. So you sent it to the TCP portion for processing. Now, TCP is done processing. It's done reliability, all of that. It has to know which application do I send this data to, right? Is it an email? Is it Slack? Is it something else? And so for that, we said we had this concept of ports or logical ports. Okay. We said a port identifies where an application process attaches to the operating system. And if you remember, we also said that port numbers were going to be carried by packet headers. Okay. At the time when we talked about this, we hadn't talked about layer 3, layer 4, and so on. So now understand that the place where you carry that port number is in the layer 4 header. Okay, so if your layer 4 implementation is TCP, then it's part of the TCP header. If it's UDP, then it's part of the UDP header. Any questions on this? Okay. And you also should be able to relate this to the sockets interface that you did in section. So now packet comes in, you look at the port number, you send it up to the corresponding application. Reliability we covered in our last lecture, so I'm not going to cover the concepts again, but just a quick recap of what we covered. We talked about the various techniques or the building blocks that go into building a reliability protocol. Things like checksums, acknowledgements, negative acknowledgements, timers, windows, sequence numbers, and so on. We also talked about different trade-offs about how you could combine these into an actual design. We'll get back to how TCP does them, but I was not going to recap them here. If anyone has questions or wants a quick review or reminder of something, now's your time. No? Good? Okay. So the last thing, not the last thing, but the next one is this notion of application layer abstractions, right? That the application does not want to have to reason about duplicate packets, retransmissions, corrupted packets, IP packets, any of that. And so instead, we want a higher level abstraction that the application is happy to reason with. Any thoughts on what would be a good abstraction for applications? There are basically 2 that are the canonical ones we've used for 30, 40 years now, but there's certainly space for more. Thoughts? What is a good, if you were writing an application on top of the internet, let's say you're transferring data from host A to host B, how do you want to think about the internet as like the service it gives you? What would make life easier for you as an application developer? Yep. Wait, sorry, I missed the last bit. So you just want to send the bytes over. What is that? What would we call that abstraction? I think I heard someone. A byte stream. So the byte stream abstraction is probably the most intuitive for many applications. So we said, and this is what TCP does, is a reliable in-order byte stream abstraction. And we're going to go into it in more detail in a bit. But at a high level, the way you can think of it conceptually is you have a sending application and a receiving application. Ideally, the abstraction you want between them is, think of it as just a pipe that is reliable, so it never drops anything, and it never reorders anything. So you put bytes into this pipe in some order, and the receiver just receives every byte in order. If that was your abstraction, you don't have to think about headers. You don't have to think about specific protocols. It's just the bytes you want to transfer. You don't have to worry about things that get lost. You don't have to worry about things that get corrupted. You don't have to worry about things that get reordered. So is it clear why this would be a good abstraction for application developers? We've just abstracted away all the complexity of the network. Does that make sense? So this is the abstraction that TCP wants to give to applications. So it's what we call the northbound abstraction. Okay? The abstraction that TCP itself has to deal with, or the southbound abstraction, is the IP abstraction of packets, of retransmissions, of things that get lost, reordered, delayed, and so on. Okay, so that's why TCP